It is a pleasure to introduce our next speaker, Anuradha Ekanaik. The title of his talk is Minimal Volume Cusped Hyperbolic Three Manifolds with a Compact Total Geodesic Boundary. Yes.
Thank you so much for the invitation, and thank you so much for organizing this session. I'm going to talk about hyperbolic three manifolds, and basically, I'm going to talk about volumes of those manifolds. So a hyperbolic three manifold is a Riemannian manifold that can be covered by open sets, isometric two open sets in H3, and the transition maps should also be isometries. By H3, I mean hyperbolic tree space. The manifolds I'm talking about, they are going to be connected, complete, orientable, and also going to have finite volume. For such manifolds, we have this structure theorem. If we take a manifold like this, we can decompose it to a thick part and a thin part. The thick part is going to be a compact part, and the thin part is going to be a collection of these objects which we call as cusps. And if the manifold does not have a boundary, or even if it has a boundary, but if it's compact, these collection in the thin part, the things we call as cusps, they are going to be homeomorphic to Euclidean 2 torus times a half open interval. So by cusp, I basically mean these things, the objects that are homeomorphic to Euclidean 2 torus times a half open interval. Right. So William Thurston is someone who studied the volume structure of this manifold very extensively. He showed the set of all the hyperbolic volumes. It is well ordered and it forms an ordinal type of omega to omega. So his result actually implies the existence of minimum volume manifolds in various different various topological classes of manifolds. For an example, this set, it will have a minimum number, and that minimum number will be the volume of the smallest hyperbolic tree manifold. So there's a hyperbolic tree manifold. Among all other hyperbolic tree manifolds, it has the minimum volume. So this point, the minimum value in this set, it's corresponding to the smallest hyperbolic volume of the smallest hyperbolic tree manifolds. Then we have limit points. So the first limit point is corresponding to the volume of the smallest one cusp manifold. The second limit point is corresponding to the second smallest one cusp manifold, and it goes on like this. And then we run into limit points of limit points. So the first limit point of limit point will be the volume of the smallest two cusp manifold. So we have this, the Thurston showed there's this nice structure when it comes to hyperbolic volumes, and it implies the existence of all these small volume examples basically in different topological classes. So that naturally started a program to identify what these things are. So Thurston's result, I think it was published in the 70s. So since then, people have been trying to identify what these minimum volume examples are. Right. So here's a list of known results currently that belongs to this category. The first one is Kayo and Meyerhoff. They showed they showed the figure-8 knot complement, and what they called as the sibling of the figure-8 knot complement. These are the smallest hyperbolic tree manifolds with one cusp. And then Ian Egel showed the Whitehead link complement and one of the Prestel link complements. They are the smallest two cusp manifold. And then in 2009, Gabay, Meyerhoff, and Milley, they completed this project. It took them around 3 decades to complete this project. They finally showed the smallest manifold among all the hyperbolic tree manifolds is the Weeks manifold. So it's a compact manifold. It takes the volume around 0.94. So they showed this is in fact the smallest hyperbolic tree manifold. Right. So the results I want to talk about in this talk, they have the same flavor. However, these examples I'm showing you right now, they are hyperbolic manifolds with no boundary. The ones I want to talk about, they will have a compact totally geodesic boundary. Right. So for the rest of the talk, I will be talking about these manifolds. They are hyperbolic. In addition, they have a compact totally geodesic boundary. They have a boundary which is going to be compact and totally geodesic under the hyperbolic structure. Right. So these manifolds, they are Riemannian manifolds, And they are covered by open sets of half spaces in H3. By half space, I mean we take a geodesic plane in H3, take the complement of that geodesic plane, and we'll have two disconnected components. We take a closure of one of those. So that's a half space, and these manifolds with a total geodesic boundary, they are covered by open sets of half spaces. And if we assume the boundary is compact and also connected, the boundary is going to be a genus G surface for some G greater than or equal to 2. I'm talking about manifolds with compact boundary. I can also assume the boundary is going to be connected, because if the boundary is disconnected, it's always going to yield a volume which is bigger comparing to the case when the boundary is connected. So we can assume the boundary is going to be connected. Right. So the universal cover of such a manifold is going to be a convex subset in H3. It's going to be bounded by a countable many half spaces in H3. If we are working on the upper half space model, the geodesic planes are going to be these hemispheres. So the universal cover of a manifold like this, it will be a convex subset bounded by countable many hemispheres. So this is how a universal cover of a manifold like this will look like. Right. So now we know the type of manifolds we work with. And now I want to explain the type of geometric block that we will need to construct them. How do we construct them, or how do we triangulate them? To do that, we'll need a special type of polyhedron in H3. So we take the setup is we take three geodesic planes, A, B, and C, three geodesic planes in H3. They intersect pairwise, but the three of them, they do not intersect inside H3. Okay. And if these three geodesic planes, if they are going to intersect on the ideal boundary of H3, we call it as an ideal vertex. So if you have a tetrahedron or polyhedron with all the vertices are ideal, we call it as an ideal polyhedron. And we use ideal polyhedrons to construct hyperbolic tree manifolds with no boundary. For an example, the figure 8 knot complement I mentioned earlier, that has a triangulation by two ideal tetrahedron. But when there's a geodesic boundary, we need a different variation of this tetrahedron. We'll need a different type of vertices. We call them as ultra-ideal vertices. So you have three geodesic planes. They don't meet inside H3. They don't also meet on the boundary. If that happens, we call it as an ultra-ideal vertex. So a polyhedron or a tetrahedron with an ultra-ideal vertex is going to have infinite volume. But there's a truncation process that kind of cut off this infinite volume part of the tetrahedron and give us something finite to work with. So what happens here is we have these three geodesic planes that forms the ultra-ideal vertex, and there's a fourth geodesic plane which is perpendicular to all three of the planes that makes the ultra-ideal vertex. So we take this fourth geodesic plane, we take the fourth geodesic plane and take the intersect of that with the tetrahedron. So we'll get a vertex which is truncated by that fourth geodesic plane. So we'll need this type of tetrahedron or polyhedra to construct manifolds with totally geodesic bound. So here's a picture of a tetrahedron which has two ideal vertices. So here's an ideal vertex. The three planes meet on the boundary here. Here's another ideal vertex. So the three planes meet on the infinity point at infinity, which is also part of the boundary in upper half space model. And these other two vertices, these are what we call as ultra-ideal vertices. So what are these shaded triangles? These shaded triangles, they are the part of that fourth geodesic plane which we use to truncate. So we had an ultra-ideal vertex at this point, and there's a fourth geodesic plane perpendicular to all three of them. So we intersect this polyhedron by that fourth geodesic plane. So this shaded triangle, it's a part of that fourth geodesic plane which we use for the truncation. Same at this end. This is part of that fourth geodesic plane we use to truncate this vertex. So we'll need this kind of tetrahedron to construct manifolds with geodesic boundary. We can identify these faces of this tetrahedron. Of course, when we identify, certain conditions has to be met to make sure the hyperbolic structure extends. Assuming those conditions are met, we can get a hyperbolic manifolds with a geodesic boundary, and these shaded triangles, the gluing of these shaded triangles across these edges, the shaded triangles forms the geodesic boundary. Right. So this is our building block, and Kojima actually showed any hyperbolic manifold with a geodesic boundary can be triangulated by these kind of pieces. Right. So we have the geometric block. Now the next question is, given a manifold, how many of these pieces do we need to construct it? Like, what's the minimum number of tetrahedra in a triangulation? This is also equivalent in this for these kind of manifolds. The minimum number of tetrahedra is also equivalent to the notion of complexity of a manifold in the traditional sense. So the question is, if you fix G and K for a given manifold with genus G boundary and K cusps, how many tetrahedra do you need to construct a triangulation of that? So the answer for this is given by these three guys, Frigerio, Martelli, and Petronio. They studied these manifolds extensively in early 2000s. So they showed if a manifold has a genus G boundary and K cusp, it will need at least G plus K tetrahedra in a triangulation. So in other words, for a fixed G and K, a manifold with geodesic boundary of genus G and K cusps will have a complexity at least equal to G plus K, right? Okay. So then they actually studied this class of manifolds that has the minimum complexity. So they call this class as M of GK. So M of GK are the manifolds with K cusps, genus G boundary, and also admit the minimum number of tetrahedra, which is G plus K. So in other words, the manifolds in this class, for a fixed G and K, these are the manifolds with genus G boundary K cusps and a minimum complexity. Okay. So why am I talking about complexity? Because the complexity is a notion very closely related to the volume. This is first mentioned by William Thurston, as far as I know. He remarked that one gets a good feeling about the volume. I mean, one get a good feeling about the topological complexity by looking at the volume. Volume is a good measurement for the topological complexity. So volume and the topological complexity are two very closely related notions. So if one is to like identify minimum volume examples, the place they should look is the manifolds with minimum complexity. So we have these sets of manifolds called as M of GK, studied by Frigerio, Martelli, and Petronio. And if one was to identify minimum volume examples, a natural place to look at is M of GK. And that's exactly what Fuji, Kojima, and Miyamoto did. Fuji classified all the manifolds in M of 2,0. M of 2,0, it means the geodesic boundary of genus 2, 0 cusps, so the manifolds are compact, and admits a triangulation by 2 tetrahedra. Fuji showed there are 8 non-isometric manifolds in this class, and each manifold has a volume around 6.45. And then later Kojima and Miyamoto showed these are the ones in M of 20 are in fact the smallest hyperbolic 3 manifolds with a compact totally geodesic boundary. So this is the only known example of a minimum volume manifold with a compact totally geodesic boundary. Later, Miyamoto published some results for manifolds with non-compact totally geodesic boundary, but my focus will be on the ones with compact totally geodesic boundary, and this is the only known result so far in that category. So what I wanted to do is to look at the manifolds with a compact totally geodesic boundary and also has a cusp. The ones studied by Kojima and Miyamoto and Fuji, they are compact manifolds. They don't have cusp. So what I wanted to look at is what's the manifold with the smallest volume that has both a compact totally geodesic boundary and a cusp. And the place to look at is M of 2,1. These are the manifolds with genus 2 boundary and 1 cusp, and also admits the minimum number of tetrahedra, which is 3 in this case. So Frigerio, Martelli, and Petronio, they studied these classes, they classified these classes for small g and k. In particular, they showed this class, M of 2,1, actually has 1 member. So that will be my candidate. That's what I believe, that's what I wanted to show, is the smallest manifold with both a cusp and a compact totally geodesic boundary. We'll call it as N naught. And it has a volume around 7.8. And also, Frigerio, Martelli, and Petronio showed this is a knot complement or in a genus 2 handle body. The main theorem of this talk is to show this manifold is in fact the smallest manifold with both a cusp and a compact totally geodesic boundary. So I'm going to give a brief outline of how we proved this, and all of this work, it's joint work with Professor Jason DeBlow. Right. Yeah, this is a picture of the candidate N naught. It's a knot complement in a genus 2 handle body. So here's a brief outline on how we actually proved this, how we actually showed this guy is the smallest manifold with both a totally geodesic boundary and a cusp. Right. So there are a couple of basic notions when it comes to the volume of these manifolds. One is a return path. A return path is a geodesic arc in the manifold between 2 points in the boundary, and at each endpoint, it's perpendicular to the boundary. So if we take a lift of a return path, it's going to be a common perpendicular to two boundary components in the universal cover. Again, if we are working on the upper half of space, this is how a lift of a written path will look like. These hemispheres are boundary components of the universal cover, and here's the common perpendicular, which is a lift of a written path. And having written paths also leads us to have these special type of hexagons we called as right-angled hexagons. So if we take three distinct components in the boundary of the universal cover, for each pair, the common perpendicular for those two will be a part of the universal cover, and we'll have these hexagons which are right angled at each vertex. So we'll have these right angled hexagons, and the alternating sides are going to be lifts of return paths. Kojima showed for a given manifold, there's only for a given manifold you can actually enumerate return paths so that their lengths are increasing. So we'll enumerate the return paths of a manifold by lambda 1, lambda 2, and lambda 3 so that their lengths are increasing. So L1 will be the length of the shortest return path, L2 will be the length of the second shortest return path, and so on. So if we take a right-angled hexagon, if their alternating side lengths are Li, Lj, and Lk, we call this as an IJK hexagon, and these hexagons will play an important role in our volume computations. Okay. Right, so here's the setup. We have a manifold with a geodesic boundary and also has a cusp. I can also assume the boundary is genus 2 because if it has a bigger genus, the volume is going to be bigger than the volume of our candidate. This follows from a result by Miyamoto. So we can assume the boundary is also genus 2. And for such a manifold, there's going to be two main components that contributes to the volume. The first is the color of the boundary. We have a geodesic boundary. We can take a color of that. And then we have a cusp. We can take a neighborhood of a cusp. So these are the two things that will contribute to the volume of this manifold mainly. Okay. For example, here's the color of the boundary. We can expand this color as long as its height does not exceed L1 over 2. That color will remain embedded. L1 is the length of the shortest return path, so as long as the height does not exceed L1 over 2, this color will remain embedded, and of course the volume of that color will be a function of L1. And then I have this cusp neighborhood. I am going to expand it till it hit the color. So we'll have this cusp neighborhood, which is the second component that contributes to the volume. So volumes of both these things are functions of L1. And also the volume of this cusp neighborhood, volume of the second part, it depends on the type of hexagons we see in the universal cover. I guess this is the picture. This is kind of an attempt to show you why that's the case, why that's believable, why the volume of the cusp neighborhood depends on the type of hexagons we see in the universal cover. Basically, if this is a boundary of a cusp neighborhood, and we can think of like fundamental domain under the action of cusp translations, and underneath that we'll see a right-angled hexagon. So whatever the right-angled hexagon we see here, that actually decides the volume of the cusp neighborhood. So it depends, volume of the cusp neighborhood depends on the type of hexagons we see in the universal cover. So we have these two main volume components. They are embedded. So the addition of their volume is going to form a lower bound for the volume of our manifold. And as I said, they are functions of L1, and they also depends on whether we have 111 hexagons or not. So it turns out if we don't have 111 hexagons, this lower bound, this lower volume bound, is always going to be bigger than 7.8. 7.8 being the volume of our candidate. So if we don't have this special type of hexagons, 111 hexagons, the volume of the manifold is always going to be bigger than the volume of our candidate. So this is the first part of our theorem. we can say if we take a manifold with a geodesic boundary and a cusp, either its volume is going to be bigger than our candidate. If not, it's going to have a pair of 1-1 hexagons like this. So this is the first part of our theorem. So that tells us all we have to do is to now look at the manifolds with this property. We look at the manifolds that has a pair of 1-1 hexagons. So for the next remainder of this talk, I'm going to talk about this part where a manifold has a pair of these special hexagons. Okay. So before I do that, let me just go back to my arrangement I showed you. So this, I use this basic arrangement to give the basic idea, but this arrangement actually leaves a lot of volume outside. So there's a volume outside that doesn't cover by both color or the cusp neighborhood. So the actual arrangement we used, it's a bit more complicated than that. We actually expand these things a bit, and then we'll have regions of overlaps, and handling those regions of overlaps is entirely a different thing, which I do not want to get into at this point. I had few slides, but I really shouldn't have included these slides because I'm not going to have time to do that. But the actual arrangement will look like this. And we have these regions of overlaps, and how we handle them, it's an entirely different thing I don't want to get into. But the basic idea will remain the same. We'll have a lower volume bound, and that depends on the type of hexagons we see. And if we don't have 1-1 hexagons, our volume is going to be bigger. So all it remains to do is to look at what happens when we have 2-1-1 hexagons. So for next 4 or 5 minutes, I'll talk about this case. So this is our setup when the universal cover actually has 2-1-1-1 hexagons. They are right angled hexagons, and the alternating sides have length L1, or alternating sides are lifts of the shortest return path. That's why we have 1-1-1. So these 1-1 hexagons are nice because if the two of them are going to intersect, this is the only way it can happen. This was a result by de Blois in one of his earlier papers. If the two 1-1 hexagons are going to intersect, they're going to intersect in this way. And they also have this nice property. The alternating sides of a 1-1 hexagon, they project onto the shortest return path, but however, everything else is going to project homeomorphically. So that's why it's important to have 1-1-1 hexagons because of this important property. So the situation is, now we have a two complex sitting inside the manifold. We have the boundary of the manifold. This is the geodesic boundary. We have the shortest return path, which I call as lambda1. And then we also have these projections of 1-1-1 hexagons. We had a pair of such hexagons in the universal cover. We have their projections. And these projections are going to be, mapped homeomorphically when we project into the manifold. So we have these two complex sitting inside our manifold. What we are going to do with these two complex is we are going to thicken it up. We are going to construct a three-manifold, a three-submanifold, which is obtained by thickening up these two complex. So we take the boundary, we take its product with the unit interval, we take the shortest return path, we take its product with a unit disk, and we take the hexagons and also take the product. So this is we take the two complex and we thicken it up basically. So we have this three submanifold sitting inside the original manifold. We call it as X of n. So this is a manifold that sits inside the original manifold. The prototype picture is this. This is the thickened up manifold. This is the tube, which is the thickened up shortest return path. And to this arrangement, we are going to attach the thickened up hexagons. Right. So this is kind of what we will get. This is again the boundary, thickened up original boundary. This is the tube, which is the thickened up shortest return path. And these are the thickened up hexagons. We attach them along this tube. So we studied what this manifold is. And we can identify three different boundary components of this manifold. There's underneath of this, there's an original copy. There's a copy of the original boundary underneath of this. And then we have these end copies of the hexagons sandwiched this sort of a vertical strip along the tube, and also this kind of part of the other side of the boundary copy. So all these things are going to form a separate boundary component, something that looks like this. And if we compute the Euler characteristic of this is going to be a torus. And similarly, we'll have another boundary component, which is going to be another torus. And also, as I said, we have the original copy of the boundary. So we have two boundary components that looks like this. Both are going to be torus. And we'll have the original boundary. So since I'm kind of running out of time, I'll just try to complete this in a couple of minutes quickly. This thickened up two manifolds, as I said, it has the original boundary, it has two torus boundary components. We were able to show this manifold has a triangulation by 4 tetrahedra. And also, we can simply show if we do a Dehn filling on this thickened up complex, we can recover the original manifold. So all we have to do is to look at the Dehn fillings of this manifold. If we can identify all the Dehn fillings of this manifold, that should tell us the smallest hyperbolic three manifolds with a cusp and a totally geodesic boundary. We constructed triangulation for this Xn, and we plugged it into a software called as Snappy, which is a commonly used software in three manifolds. And Snappy tells us the volumes of all the Dehn fillings of this manifold. And it turns out, except 6 Dehn fillings, all the other Dehn fillings are going to be non-hyperbolic or yield hyperbolic manifolds with volumes bigger than the candidate. And there are exactly 6 Dehn fillings. That's going to yield a manifold which has the same volume as N naught. And they are almost there. To wrap things up, we will need this result from Frigerio, Martelli, and Petronium. This result basically tells us all these 6 Dehn fillings we got from Snappy, which has the same volume as our candidate. This result tells us these 6 Dehn fillings are actually equal to our candidate. So there cannot be anything else. This result by Frigerio, Martelli, and Petronio, they tell us the 6 Dehn fillings we got from Snappy, all 6 should be actually equal to our candidate. So that is basically the conclusion of the project. This is the conclusion of the second part of this result. If we have a pair of 1-1-1 hexagons, then either the volume is going to be bigger than the volume of our candidate, or it has to be exactly equal to the candidate. So this basically concludes the project. This tells us the candidate was actually the correct candidate. It was the smallest volume manifold with a totally geodesic boundary and a cusp. For some reason, I thought about talking about all extending this work when there are multiple cusp cases, but that was too ambitious. So I'll stop here. Sorry about going over time. Thank you.